Hi, my name is Venkatesh R. Mahadevan, and today I'll be presenting a summary of the paper titled EIE Efficient Inference Engine on Compressed Deep Neural Network. The authors of this paper are Song Han et al. The goal of this presentation is to describe the architecture presented in the paper and to briefly summarize the results of implementing the same. So let's get started. Traditionally, machine learning in hardware has been implemented using a four-step methodology. The first step involves a neural network representation using well-known architectures such as AlexNet, VGGNet, etc. The second step involves the creation of a software model using high-level APIs such as Keras, TensorFlow, PyTorch, etc. The third step involves high-level synthesis, which basically converts the software model into RTL form. The fourth step involves the programming of the RTL code into a specific DNN accelerator of choice. However, there are several limitations that are encountered in the process of doing so, namely limited resources, power and area budgets, scalable hardware platforms, and sparsity exploitation. Matrix vector operations, which lie at the core of machine learning and which are often used in the fully connected layers, require a lot of hardware multipliers. The weights that are used for the same operations require lots of memory. Power and area budgets for modern AI chips are often quite stringent, and therefore energy consumption needs to be monitored. As can be clearly seen, a 32-bit DRAM operation requires 6400 times more energy than a 32-bit add for the same data types. The third challenge that is faced is with regards to scalable hardware platforms for different types of machine learning models. The fourth challenge that is faced is with regards to sparsity exploitation for weights and activations. As can be clearly seen, the performance of AlexNet is greatly increased by fine-grained pruning for both weights and activations. The architecture that is proposed in the paper has three key features. The first feature is regards to the compression of the weight matrix. The second key feature is that the encoded weight matrix is stored in a compressed sparse column format. The third feature is that the computation is parallelized by interleaving of the weight matrix over multiple processing elements. The pruning and weight sharing process involves finding out the non-zero entries of the activations in the weights and performing operations using the same. As can be seen over here, the activation matrix contains both zero and non-zero entries. The weight matrix is uniformly distributed over all of the processing elements. The activation matrix is then multiplied with the weight matrix to produce the corresponding non-zero output. Therefore, A2 would be multiplied with W22 and W12 B0 on the other hand is a result of the sum of the products of the activation matrix with the weight matrix that is allocated to processing element 0. In this method of deep compression, only non-zero entries of W and A are used. Only 4 bits are used to represent W, and since only the activation changes, we always have a cache hit for the weight. The process of detecting the non-zero activations and weights takes place via an element called as the leading non-zero detection node, whose main job is to detect these non-zero entries and to forward them to the processing elements downstream. Each processing element stores these non-zero activations and weights into its activation queue, which is then stored into the even and odd SRAM pointer banks. These are then used downstream to perform the calculations, and the result is stored into the ACT SRAM. The implementation of EIE shows that EIE is faster than its counterparts by a huge amount. For example, EIE is faster than its CPU counterpart by 189x, by 13x when compared to its GPU counterpart, and by 307x when compared to its mobile GPU counterpart. The performance is comparable to the desktop GPU in the batching case. The giga operations per second are reduced by 97%, and EIE can be used along with model compression to achieve an even higher speedup. Thus, in summary, the fully connected layers of neural networks perform matrix vector operations. They are memory limited and consume lots of energy. EIE can reduce the energy consumption by 3400x compared to the GPU. It does this by exploitation of sparsity in activations and weights and through weight sharing and quantization. High performance is guaranteed for most modern-day FC layer benchmarks. An option that the authors could have explored in this paper was whether EIE could benefit from a log-normal representation of numbers without loss of accuracy. For further details, please refer to the paper. Finally, I'd like to thank AIC and Janmeja Channegowda for providing me with valuable inputs for refining this presentation.